right, next lecture in the series, we are talking about free body diagrams, FBD, and also forces. So a free body diagram is a diagram that describes an object. We can just dot it, and it describes all the forces that act upon a certain object. So we could have a force going down due to gravity. We could have a force going up, which is the normal force, which is just the gravity, the ground pushing back on the force. They should be equal. It can also have like an applied force, like a car that's accelerating or pushing it. We could have a force going this way, which is due to friction, and we could have all sorts of other forces. A string pulling it in this direction. Many different forces in different directions that it can go. And so a free body diagram just describes what all the forces are and their magnitudes, so we can make up like magnitudes mg. This is also mg. This could be just 3 newtons, and this is like mu times n, all sorts of stuff. And they're used to many applications, such as like calculating a particle in equilibrium, such as when say this tension was instead going this direction, we can measure all the forces in the x direction and set them to 0, and then calculate what some of the forces are, knowing that all the forces going this way have to equal the forces going that way. And just to get to different scenarios, like the classic hill scenario, this has a degree angle theta. We have a mass going here, and we have the gravity force mg, and we want to know how much force is going to be pulling it down the hill, or what rate it accelerates. And this, the idea here is to separate it into components. So this gravity vector can instead be expressed by a inward vector here, and a downward vector here. And to calculate the value of these vectors, we just use the theta here. We know that theta here is going to be equal to the theta, to 90 minus theta, because of similar triangles. Or I guess we could say this is theta, and this is 90 minus theta. I don't have time to write it in, but based on the trigonometry, this component going down the slope is equal to mg sine theta, and the component going this way is mg cosine theta, based on its right triangle trig. And now we know that like the normal force is going to cancel out, so we can draw force in this direction, which is the same thing as that. And then we just know that going down the hill is mg sine theta, and we can divide by m to get the acceleration being g sine theta. This is assuming that there's no friction. And so this is generally how free body diagrams work. You can add up forces and set them equal to each other when we know it's in equilibrium, and use it to find accelerations and all sorts of things. So yeah, it's free body diagrams. Pretty important concept, basic to a lot of other things. Our massless frictionless pulley, frictionless surface here, 2 masses, one's on an incline, one's free hanging. And this question asks, what is necessary to always make sure that this slides down, basically, and this gets pulled up? What are the conditions where that always happens? And so we can start filling in our free body diagrams. For M2, we have just mg, or m2g, in the downwards direction. And in the upwards direction, it has tension here. And we know that since it's in equilibrium, tension must equal mg, or m2g. So we know that this tension is m2g. And we know that in order for this to move down the ramp, or accelerate down the ramp, is that the force pulling in this direction, this tension, has to be greater than this tension. That's the only time where it's going to accelerate downwards, is if this tension pulls harder, basically, than this tension pulling this way. So to find the tension in this string, we draw a free body diagram for this. This goes straight down, m1g. But we want to separate the forces, or separate the components, because it's at an angle. So this component is going to be mg sine theta, and this component is going to be, this component is going to be mg cos, sorry. And this is going to be mg sine theta. We know that this is going to get canceled out by the normal force. We don't really need to worry about this, but this downwards acceleration or force of mg times sine 30 degrees is the angle here, is what's going to be pulling this force in this direction. And we know that in a frictionless pulley, the tensions will always equalize. So on this side, I should have said it earlier, but this is also going to be m2g. So in this mass 1 free body diagram, we have pulling on this side is mg sine 30, or basically 1/2 mg. And on this side, a force of m2g is going to be pulling on this side. And so in order for m1 to accelerate down the ramp, we need this force, mg sine 30, to be greater than the force pulling it up the ramp, which is m2g. So if we have mg sine 30 is greater than m2, I guess, g, this should be m1, then we cancel out the g's, and we get m1 sine 30 must be greater than m2, which is the third answer choice. And of course, this is the only time where it guarantees this will happen. So this is the answer.